Hello, my name is Ewan Ha, and I go to Appleby College in grade 11. The title of my project is using K-Wave to simulate ultrasound for optimal intravascular ultrasound device frequencies. So the problem that my project is looking at are cardiovascular diseases, which are the leading cause of death for many years. You can see with the table on the right, the annual number of deaths in 2016. Cardiovascular diseases is the leading cause by a large margin. In fact, 17.65 million people died due to cardiovascular diseases in 2016, and it only increased in 2019 to 17.9 million deaths. Ruptured atherosclerotic plaques is a major cause of many of the issues cardiovascular diseases are known for, such as heart attacks. So what is atherosclerosis? Well, it's the thickening or hardening of tissues of the vessel wall that can lead to reduced blood flow and oxygen supply or blockages. This begins with damage to the endothelium, which is the inner layer of the vessel wall, due to high blood pressure or inflammation. Buildups can occur between the intima and adventitia layers of the blood vessel with materials such as cholesterol, fats, cellular waste, calcium, and fibrin. This is a slow, progressive disease that can start even during childhood and affects a large population. So common diagnostic tests for this disease are usually external. For example, angiograms are used with a special dye and x-rays to show a general overview of arteries of your heart. You'll see how on the left, you can generally see how the vessels have thickened and reduced the blood flow compared to normal blood vessels on the right. Chest x-rays are also used, which use a projection radiograph of the chest to highlight calcified plaques. However, it only is used for a specific type of plaque, which makes it a bit limited and still just gives a general overview. However, in situations when there's a need for more detailed and quantified measurements of the plaques, these external diagnostic tests would not work. That is why the intravascular ultrasound, or IVUS, exceeds in this field because of its ability to give more detailed images. This is because, as I'll play this video here, it uses a catheter attached to a tube that is inserted within the arteries itself towards the general area of the plaque. It can then physically rotate the catheter in a mechanical IVUS, which release ultra waves which bounce back from the material it hits, such as plaques. So once the ultrasound bounces back from the materials, it would then be absorbed by the catheter again, which it can then send to machine and create these images. The two main parameters that our project is looking at are the image resolutions as well as the penetration depth of these signals, which give its image qualities. However, although there are many upsides of IVUS, there is one main issue. This is the physical limitation of IVUS. For example, with high-frequency ultrasound, such as the 80 MHz image, it can offer a high resolution, which is shown by the clearer edges compared to the 30 MHz image, which is much more hazy, but it suffers stronger attenuation, which means for the 80 MHz image, it does not have as large of a field of view as the 30 MHz image, so the image cannot give as much information. This is important because with varying plaque shapes, sizes, and depth, it is a challenge to quickly decide the optimal frequency for IVUS diagnosis. In the past, there has been work done to try and address this issue. For example, for multi-frequency IVUS devices, they have combined low and high frequency catheters to make up for this issue. However, they use physical props for the device, such as physical catheters, as well as physical mimics of the plaques to do these experiments, which result in high costs. Virtual simulations have been experimented with in response to these high costs, and people have experimented with custom IVUS ultrasound models by creating their own formulas or comparing types of tissues with image quality. Our work focuses on virtual simulations due to the cost limitation. However, our project is unique because it can systematically study the impact of different transducer frequencies on different plaques for imaging performance. We have developed a simulation platform for IVUS imaging in various environments. And the reason that our project is important is because it can produce data in an environment where there's a lack of existing data showing correlation between frequencies and image quality. The way our simulation is produced is from a K-Wave toolbox from a popular language called MATLAB. It can then simulate the time domain ultrasound propagation, which is perfect for IVUS ultrasound propagation in complex and tissue-less media, which can mimic plaques. The method that we have used to create the simulation have been put in a few steps. Firstly, we created the simulation background, which you can think of as a sandbox where all of the simulation occurs in. We then define the target parameters, which is the size and shape of the plaque. We then created the transducer, set its size, as well as the scanning step, which is how often it will scan the environment. We will then set the ultrasound frequency, which can be adjusted between experiments. And finally, we run the simulation, acquire the signals, and then create the final images for comparison. So this is an animation showing how this works. So this black bar represents the transducer, and the colored waves that propagated from this black bar are representing ultrasound waves. If you look closely, there was waves bouncing back around here, which means propagation since there was an invisible image target here. We have shown the work of simulation with this image target of 3 bars as the ground truth and the image result of 3 bars, which appeared consistently with the target image. We have shown that imaging responded to frequency adjustments, as well as we had the ability to adjust the phantom shape and size, which is important for different experiments. We have also shown that our program is consistent with background research. You can see how we have created 2 different image targets, the 3 bars as well as a circle. We have also used 3 different frequencies, 2 megahertz, 5 megahertz, and 15 megahertz frequencies. This is important because we showed that higher frequencies have higher detail due to its clearer edges. However, there was less penetration depth because the signal got weaker or darker closer to the bottom compared to the 2 megahertz images. In conclusion, we succeeded in building an IVUS imaging simulation platform that allowed for the change of frequencies as well as the study for a wide range of phantom parameters. This is important because this allows for easy access to a simulation that can compare images with these 2 parameters. In the future, we look to build a user-friendly interface that allows more people to access this in a more intuitive way, as well as have a simulation that is compatible with the recent multi-frequency IVUS device exploration. Thank you for listening.